When finding the derivative of a function, it will sometimes be necessary to use a method that's called implicit differentiation. So at the end of this lesson, you'll be able to use implicit differentiation to find the derivative of a function. All right, let's take a look at an explicit form of a function. Explicit means that you can actually just type the x in and you get your y. Notice it says y equals. We've dealt so far with everything in explicit form. Well, sometimes you'll have functions in implicit form where, notice, it's not specifically solved for one variable. We have x's and y's happening on the same side. So one way that we could approach this is we could actually solve this equation for y. And if I did that, let me just show you here. Minus x squared. Then I'd have to square root. And actually I'd have to enter and introduce a plus or minus. And now notice, when I want to take the derivative of that, it would involve using the chain rule and the power rule and lots of different rules, and it just becomes a more difficult process to find the derivative of. So when something is in implicit form, we can actually use implicit differentiation. There are steps right here that we will refer to as we're going through. I'm not specifically going to mention them right now, but I actually will be using them in our examples. So let's go ahead and find the derivative. So this one says to find dy dx, which is to take the derivative, and when we're doing this, this is really taking the derivative of y with respect to x. That's what that means. So what we're going to be doing on this one, and I'm going to show you kind of where this dy dx comes from. When we take the derivative of x squared, notice we just usually get 2x. I'm going to show you what we really should be writing, but we don't write it, and there's a reason. I'm really taking the derivative of x with respect to x. So notice I get dx over x, which is just 1. That's why we never write that step. That's why we always just put 2x. All right? But now the next one, the derivative of y squared is 2y, but we're taking the derivative of y with respect to x. So that's why I write that notation right next to it. And then equals the derivative of 16 is 0. Notice the problem asked me to find dy dx. So when I do this, we're just going to be solving for the dy dx. So I'll subtract 2x from both sides. So get negative 2y equals negative, dy dx equals negative 2x. And then if I just divide both sides by negative 2y, I will get dy dx equals x over y, and that would be my derivative. Just one thing I want to point out, don't forget that when we have like y equals x squared plus 8 or something like that, when we take the derivative, we either call this dy dx or y prime. That's exactly this whole step, the dy dx. So, all right, implicitly, let's go ahead and find the next one. We'll just, again, take the derivative of each part separately. The derivative of 2x squared will be 4x, and then plus the derivative of 3y would be 3, but we're taking the derivative of y with respect to x. We need to make sure that we include that. Then equals the derivative of 9y squared would be 18y, and again, we're taking the derivative of y with respect to x. Okay, now you'll notice this time, if we're wanting to find dy dx, what I would like to do is to get my dy dx's on the same side. So I'm going to subtract 3 dy dx from both sides. So when I do that, I'm left with 4x equals 18y dy dx minus 3 dy dx. All right, now I notice if I'm solving for dy dx, both of the parts on the right side have a dy dx in them. So I'm actually going to factor out that dy dx. And so when I do that, I'll be left with 18y minus 3. And now notice that I have dy dx times another quantity. So to get rid of multiplication, we can actually divide both sides by the 18y minus 3. So we will end up getting dy dx is equal to 4x over 18y minus 3. All right, let's try a few more examples. Let's say I have the sine of x plus 2 cosine y equals 1. Again, because there's an x and a y, we'll use implicit differentiation. We'll take the derivative of both parts. I know that the derivative of sine x is equal to the cosine of x. And then the derivative of the cosine of y is equal to negative sine y, so it will be negative 2 sine y, but I am taking the derivative of y with respect to x, and then equals the derivative of 1, since the constant is 0. Okay, and if I want to solve for dy dx, I'm actually going to add 2 sine, whoops, I forgot my y there, sine y dy dx to both sides. And the reason I decided to move that, because then I wouldn't have a negative, otherwise I'd have two negatives. So now I'm going to have cosine x equals 2 sine y dy dx. And now to get my dy dx by itself, I'll just divide both sides by 2 sine y. And so I'll get dy dx equals cosine x over 2 sine y. And so that will be my derivative. All right, last example for this one. Let's say I have x squared y plus y squared x equals -2. Again, it's an implicit problem because we have x's and y's both happening. So we're going to take the derivative of each part separately. The problem is, you'll notice on this one, when I look at this first one, it's actually a product of two different functions. So we're going to call the x squared f and the y g. And so now I'm going to use the product rule. So first of all, I'll identify what my f prime is. That would be 2x. And I'll identify my g prime. And in that case, it's going to be 1. But remember, I'm taking the derivative of y with respect to x. So now when I go to use the product rule, it will be f prime times g. So it will be 2x times y plus f g prime. So it will be x squared times 1 dy dx. So that's the first part. And then for the second part, we're going to do that same thing. This time my f will be y squared, my g will be x, so I'll get f prime equals 2y dy dx. G prime will equal just 1. And now I'm ready to use the product rule, so I'll have f prime times g, so 2y dy dx times g, which is x, and then plus f times g prime, so y squared times 1, and then equals the derivative of -2, since it's a constant, is 0. Okay, before I do anything else, I'm going to clean this up a little bit. This is actually going to be 2xy plus, this will just be x squared dy dx plus, when I have 2y times x, I'm going to rewrite that as 2xy dy dx plus y squared times 1 is y squared equals 0. Okay, now I notice that I do have some parts that have dy dx's in them and some that don't, and since I would like to get the dy dx by itself, I'm going to get rid of everything that does not contain a dy dx. So I'm going to subtract 2xy from both sides, and then I'm also going to subtract y squared from both sides. So when I do that, I'm going to have x squared dy dx plus 2xy dy dx, and that will equal -2xy minus y squared. Okay, next step, since these both have a dy dx, we're going to factor that out so I can solve for it. When I do that, I'll get x squared plus 2xy, and that will still equal -2xy minus y squared. And then from here, to get rid of the x squared plus 2xy, since it's multiplied, we will divide both sides by x squared plus 2xy. Okay, so my final answer will be dy dx equals -2xy minus y squared all over x squared plus 2xy. One more thing that I could do if I really wanted to, in the numerator, I noticed that they both have a negative and a y. So if I factored that out, I'd actually get 2x plus y. And then down below, they both have an x, so I could factor out an x, and then I would get x plus 2y. So either of those answers would be acceptable, though, for the derivative. So hopefully now you can use implicit differentiation to find the derivative of a function.